1.3 measurement. Scientists often work with very large or very small numbers. Astronomers estimate there are 200 billion stars in our galaxy. Scientific notation is a way that we can express a value as the product of a number between 1 and 10 and a power of 10. For example, the speed of light is about 300 million meters per second. So imagine writing that number over and over again. You'd have to write a ton of zeros. We use scientific notation, and we can say that it is 3.0 times 10 to the 8th meters per second. The exponent 8 tells us that the decimal point is really 8 places to the right of the 3. Tomorrow you're going to practice this, and so I'm going to have another video with more detail about this topic for you to watch tomorrow. For numbers that are less than 1, like small decimals that are less than 1, that are written in scientific notation, the exponent becomes negative. For example, an average snail's pace is 0.00086 meters per second. In scientific notation, that would be 8.6 times 10 to the negative 4. The negative exponent tells you how many decimal places there are to the left of the 8.6. So scientific notation becomes useful when we are multiplying or dividing numbers that are really big. To multiply numbers written in scientific notation, you multiply the numbers that appear before the multiplication sign. So here it will be 3.0 times 5, you get 15. And you add the exponents. So in this example, you would add 8 and 2, and so you're going to get 15 times 10, you keep the times 10, to the 10th. The following example demonstrates how to calculate the distance light travels in 500 seconds. And so trying to multiply 300 million times 500 would be really a difficult task, but we can pretty much break this down into very simple math. And then this number, when we're using scientific notation, we always need a number between 1 and 10. So this is not correctly written. We need to move our decimal place one more spot over so that it is in 1.5 times 10 to the 11th power. And this is about the distance that exists between the sun and the earth. Same thing when we divide. It's very similar, but we kind of do the opposite. And so when we divide numbers in scientific notation, you divide the number that is before the multiplication sign. So 1.5 divided by 3, and you get 1/2 or 0.5. And then you subtract your exponents on this. So you're going to do 11 minus 8, and you get 0.5 times 10 to the 3rd power. Again, this number needs to be a number between 1 and 10. And so we would move our decimal place one more spot over to the right, and that makes our exponent become 2. So 5.0 times 10 to the 2nd. Again, tomorrow you're going to have a video just about scientific notation. If you're not sure about it yet, that is perfectly okay. We'll clear that up tomorrow. Scientists they all use a set of measuring units called the SI system, the International System of Units. SI is an abbreviation for Système International des Units, which is French. SI is a revised version of the metric system, and it was originally developed in France in 1791. The reason why it's important is because scientists all over the world share their work with each other, and they work together. And so instead of having, like in the U.S., we measure things in feet and inches, and in France, they do something else. We all use the same thing. So scientists around the world use the same system of measurement so that they can readily interpret one another's measurements. If you told one of your friends that you had finished an assignment in 5, it could mean 5 minutes, 5 hours, even 5 seconds. So we always express numbers express measurements with in a number and a unit so that we are clear in what we are discussing. The students in this picture are taking temperature, and so they're doing a temperature measurement, which will include a number and the unit degrees Celsius. So the SI system is based upon 7 metric units, and these are known as the base units. In SI, the base unit for length, or the straight line distance between 2 points, is the meter. The base unit for mass, or the amount of matter in an object, is a kilogram. Here's a table with all of the 7 base units. In this class, we'll mainly worry about length, mass, time, and maybe sometimes temperature. There are additional SI units that are called derived units, and these are made out of combinations of base units. So basically, if you're going to do any sort of a calculation like speed is distance divided by time, that's a derived unit, meters per second. Volume is another one. It's the amount of space that's taken up by an object. We have to do a calculation to get volume, generally. Density is another derived unit, and so density's formula is mass divided by volume. And so the unit for density is going to be some mass unit over some volume unit. Usually it's grams per milliliter. So here's some examples of derived units: area, square meters, volume, cubic meters, density, kilograms per cubic meter. Energy is one that we will focus on in this class, is a joule, and so on. To derive the SI unit for density, you can divide the base unit for mass by the derived unit for volume. Dividing kilograms by cubic meters yields the SI unit for density, which is kilograms per cubic meter. So basically, if you do a calculation, you can get the derived unit. A bar of gold has more mass per unit volume than a feather, so gold has a greater density. The other thing with the SI system is that it's based off of metric prefixes, and so the metric unit is not always a convenient one to use. A metric prefix indicates how many times a unit should be multiplied or divided. We are going to spend a whole couple days working on converting metric units. But basically, the entire metric system is based off of multiples of 10. And so in the middle here, you would have a base unit, and then you can go up and have these prefixes like kilo means 1,000, mega means 1,000,000, or you can go down, centi means 100th, milli means 1,000th, and so on. For example, the time it takes for a computer hard drive to read or write data is in the range of thousandths of a second, such as 0.009 seconds. Using the prefix milli, we can write that number as 9 milliseconds instead of worrying about those extra zeros. Metric prefixes can also make a unit larger, so 12,000 meters can be written as 12 kilometers. Metric prefixes turn up in non-metric units as well. If you work with computers, you probably know that a gigabyte refers to 1 billion bytes. A megapixel is 1 million pixels. And so when we're converting, we can use what's called a conversion factor. And a conversion factor is a ratio of equivalent measurements that are used to convert a quantity expressed in one unit or to another unit. To convert the height of Mount Everest, which is 8,848 meters, into kilometers, we could multiply that by a conversion factor. And here is an example. To convert 8.848 kilometers back into meters, we would use the opposite conversion factor. And here's an example of that. So some other things we need to know about measurement is measurements aren't always perfect, and there are limits to measurement. And the first limit we're going to look at is precision. Precision is a gauge of how exact a measurement is. Significant figures are all the digits that are known in a measurement plus the last digit that is estimated. The precision of a calculated answer is limited by the least precise measurement in the calculation. For example, if I take 3 measurements and I get 3 different numbers, and I calculate something with those numbers, then my answer cannot be more precise than the measurements I took. When I talk about precision, or when I think about it, I usually say think about how many decimal places it goes to, or how small of a unit does it go to. So a more precise time can be read from this digital clock because it goes down to the second than it can from this analog clock, which measures to the nearest minute. So the smaller unit will get you a more precise measurement. If the least precise measurement in a calculation has 3 significant figures, then the calculated answer can have at most 3 significant figures. And here's an example. This one has 4, this one has 3, so when we calculate with it, we have to round at 3 significant figures. Another limit to measurement is accuracy. And accuracy is the closeness of a measurement to the actual value of what is being measured. So with precision and accuracy, precision is how close are your measurements together. If I measure the length of this pen and I get the same exact answer every single time, then I'm precise. But if I measure this length of this pen and I get an answer that is not the actual measurement, then I'm not accurate. For example, a digital clock that might be running 15 minutes slow. Although the clock would be precise to the nearest second, the time would not be accurate. And the last thing we're going to talk about with measurement is measuring temperature. A thermometer is an instrument that measures temperature, or how hot an object is. Here's a picture of a thermometer. Generally, you're going to have some sort of a scale that is in steady increments. There's going to be colored liquid in the capillary tube, and it's going to rise up to whatever temperature that the correct temperature is. Here's another picture to kind of show it. Sometimes we have lines that are really close together. This would be called a compressed scale. Sometimes that are more farther apart, easier to read. So the 2 temperature scales that you're probably most familiar with are the Fahrenheit scale and the Celsius scale. We generally talk about temperature like when you're watching the weather. They're going to be saying that in Fahrenheit. And then in science class, we're generally going to talk about it in Celsius. A degree Celsius is almost twice as large as a degree Fahrenheit. You can convert from one scale to the other by using one of the following formulas. So if I was trying to convert from Fahrenheit to Celsius, I would use this formula. If I was converting from Celsius to Fahrenheit, I would use this formula. The SI base unit for temperature is a Kelvin. A temperature of 0 Kelvin refers to the lowest possible temperature that could ever be reached. In degrees Celsius, this temperature is negative 273.15 degrees Celsius. To convert between kelvins and degrees Celsius, we use the formula degrees Celsius plus Kelvin. The degree Celsius scale is basically just created to have smaller numbers. So we don't want to be dealing with negative 273 degrees when we could talk about 0 degrees. So here are some common temperatures of things that we should know. You know what the general temperature is. We should know that water boils at 212 degrees Fahrenheit, which is equal to 100 degrees Celsius and 373 Kelvin. Normal human body temperature is 98.6 degrees Fahrenheit, which would be 37 degrees Celsius and 310 Kelvin. Water freezes at 32 degrees Fahrenheit, which is equal to 0 degrees Celsius and 273 degrees Kelvin.